So what we're going to do for each of these definitions is we're sort of going to have a colloquial definition. It's not a pure math definition so that we don't have to go into all the intricacies, but we can get the basic idea. And then from that basic idea, if we ever run into issues that are sometimes out of the ordinary, we can look at that. Okay? A line that cuts through a curve, usually at 2 points. So if you had a parabola, a secant line would cut through it like that. But you could have a secant line cutting through, like a secant to a circle, cuts through the circle at 2 points. Depending on the graph you have, it might be that you have a cubic and you have a line that cuts through at 3 points. But the idea is that it's cutting through a curve rather than just touching the curve. Because a tangent line is a line that touches a curve at 1 point and usually does not cut through the curve. So for example, you first had circles. That's the first time you saw a tangent. And a tangent touches the circle only at 1 point, whereas the secant would cut through the circle. But you can also have a tangent to a parabola, where it touches the parabola only at 1 point. You could also have a tangent to a cubic equation, and there's one special tangent on a cubic equation where it touches the point only once right here and actually cuts through it. But generally, as far as thinking of it, you can try to imagine putting a line up to a curve so that it touches it only once and usually doesn't cut through that curve. The x cubed at 0 is a special case. So there's two types of rates of change that we're going to look at. First one is an average rate of change. If it is 200 kilometers from here to Brandon, which it is exactly, which is kind of crazy. And there's a sign just outside of Brandon where it says you are 22 kilometers from Brandon and 222 kilometers from Winnipeg. And it's just very interesting to see all those twos on one sign. Anyways, you can tell I was driving on the weekend. Average rate of change. If it is 200 kilometers to Brandon, and I got there in 4 hours, what was my average speed? .50 kilometers an hour. Not very fast. I should have probably been driving faster on the highway. Okay? That does not mean that I drove 50 kilometers all the time. As soon as I left my house, jumped in the car, boom, instantaneously at 50 kilometers an hour, and I did not stop going through all the signs through Winnipeg or at any signs through Headingley, just stayed at 50 because I needed to get there in exactly 4 hours. So I set my cruise at 50 and did not change it. That would be a bad thing, right? But sometimes I might have been going faster, sometimes I might have went too fast, and then there's a time where I was driving 0 because the police officer had to remind me that I shouldn't be going that fast. But on average, if it took 4 hours, my average speed would have been 50 kilometers per hour. So here is the little graph. Okay? Here's time. You don't have to draw this, but this is time, and here is speed, okay, in 4 hours. Or here, I'll do distance, actually. I'll put distance here. Here's distance, and here's time. And in 4 hours, I started right here at Winnipeg, which will say this is my distance from Winnipeg. And Brandon is 200 kilometers an hour, 200 kilometers away, not 200 kilometers an hour. And that's where I would end up. That doesn't mean it has to be a straight line, right? Sometimes I could be faster, sometimes I forgot something at home and then I had to go back and whatnot. This could be what happened. Like, oops, I forgot something at home. Almost get back home to realize, oh, I have it. And then start driving back to Brandon again. And that might be why it takes 4 hours. Now, if I make a secant line from the start to the end, it may cut through my curve many times. It may only cut through the curve at the 2 points that I choose. But if I find the slope of this line, I have a rise of 200 and a run of 4. 200 over 4 gives me my average rate of change. So an average rate of change is just the slope of the secant over an interval. An instantaneous rate of change, that's when I would look at this moment, my speedometer is saying 100 kilometers per hour. At that instance, that's what I'm going. And an instantaneous rate of change would be the slope of a tangent line at a point. So now if we would go back to our graph before, and we would choose a point on our graph. Let's say I choose this point right here, and I drew a tangent line, the one and only tangent line that hits that point. If I would figure out the rise and run of that red line, that would tell me my instantaneous speed at that point. And I would know how fast I was going looks like about 45 minutes to an hour into my trip. And then here, say at this point, I would have a negative slope. That would mean I'm heading back home, because my speed would be a negative speed, which just means my direction has been changed. And so any point on here, I was going really fast right here. My goodness. That looks almost dangerous. Any point, if you could draw the tangent line, then you would have the instantaneous rate of change there. And then we have all of these different ways of writing rate of change. You've dealt with it most in the past as slope. Here's your slope formula, right? Sometimes you just remember this as the change in the y is your rise, and the change in your x is your run. Have you used the little triangles in physics? What do you call the triangle? Delta. They don't say triangle y and triangle x. You could, but all delta y means is change in y, change in x. And this idea of the change in y and change in x can also be written as dy over dx, and that's an instantaneous change in y over change in x, and that's called the first derivative, and what the basis of calculus is about. So the idea being with calculus is we're interested in what's happening at a moment. How fast are you going at that moment? How fast is something changing at a certain time? Because if we know how fast it's going at that time, we'll know how it's going to predict later on. So here we can make our own graph up. Let's pick some. Let's say Jack is going to school, and this is distance from Jack's house. And we'll put time down here. Let's see what happens. I mean, you're in grade 12, but it was one of those days where he's going towards school and then got lost, confused, finally saw a friend's house that was a landmark, and then ran all the way back and managed to get to school 7 hours later, just in time for calculus. Hate those days. So if that's 7 hours later, then I guess I should put a scale here. 1, 2, 3, 4, 5. Wow, that actually was pretty good. Usually my time slots start to vary a little bit when I'm doing that, but this is 1, 2, 3, 4, 5, 6. And we should put some, how far away from school do you live? Yeah. A couple kilometers. Okay, we'll put 3, and then this would be 2, and this would be 1. Okay. So we got some crazy things happening in this graph. So what this is looking at here is we're going to try and calculate the average rate of change of y with respect to x over these following intervals, x from 1 to 3. So dots on here. Here is 1. Here is 3. Okay. 1 to 4, there's 4. And from 4 to 5. So we're going to label these points, just estimate them. We've got 1, 0.75. We have got 3, we'll call that 1.2. 4, 0.8. And 5, we'll say that's also at 1.2. Just to make this a little bit more interesting, I'm going to change this last interval from 4 to 5 from 3 to 5. So if we were trying to find the average rate of change from 1 to 3, we could draw our secant line from 1 to 3. We can make a triangle so that we could see the rise and the run. And if we looked at our change in y over our change in x, well, our y has gone from 0.75 up to 0.2, so there has been a rise of 0.45. And our run from 1 to 3 has changed 2. And if we would put this in right now, 0.225, and this is where you got kilometers here and time hours. You're not going very fast. It was a slow day. I guess if you get to school in 7 hours, you would expect not to be walking very fast. But you were going about 0.225 kilometers per hour. Part of the reason that's slow is you had got lost right around 2 hours. Then from 1 to 4, I'll draw that in a different color. If we went from 1 to 4, man, not making very much progress at all during that point. Again, our change in y, you went from 0.75 to 0.8, so 0.5. And our change in x, 0.05, thank you. And our change in x is 3. And that'll be something like 0.0167 or something crazy like that, kilometers per hour. Things are not looking good at all. And finally, since I changed it to 3 and 5, the reason I did that is because between 3 and 5, we made no progress whatsoever. even though the change in x is 2. So his average speed over those 2 hours was nothing. Could have just stood there and got the same amount accomplished. So this is average rate of speed. Okay? There are points on here where Jack is like almost subhuman. If I would take this point right there and draw the tangent line that just touches it at that point. And we calculated the slope of this line by going over 1 and figuring out how much we would go up. In this, it doesn't even look like that much, but there are some steep points to this that you might have been running 150 kilometers per hour. Once you realized I could miss calculus class, stepped into an extra gear and made sure that you got here, which is great. So all we're doing is figuring out the slope. Another word for slope is gradient. Sometimes textbooks use these different words. Have you ever heard the word gradient used outside of today's class at this moment? Yes? Where have you seen it? In aviation? They also, okay. They also use it sometimes in roads. Like if there's a very steep, road coming up, they'll say the gradient of that road coming up is an 8% increase and different things like that. All right.